Okay, guys, today we're going to be talking about exponential functions. And the identifying feature of an exponential function, what makes it exponential, is that there is a constant multiplier. And let's remember that linear functions have a constant rate of change. That is not what this is. This is when each successive term is being multiplied by the same number over and over and over again. And this will come up in a lot of real-world situations. If you are at all interested in money or being rich or not being poor, exponential functions are going to come up a lot, as we'll see in our next lesson, all the different ways that they come up with money. So this is something that we're going to want to know about. It comes up in plenty of things that aren't money as well. It comes up anytime where the more of something you have, the faster it grows based on the previous amount. And we'll see that in a little while. The parent functions, unlike other functions, there are a bunch of different parent functions for this. I'm going to write y equals a to the x, where a is a constant that is greater than 0. Okay, so this could be something like y equals 3 to the x. A is a constant, so 3 is a constant. Y equals 7.5 to the x. This is fine. Y equals 1/2 to the x. Any constant that is a positive number to the x makes an exponential function, and these are all parent functions. So these are all considered parent functions. And one thing that all of these parent functions are going to have in common is they will all have the same point. And that point is when x is 0. Anything to the 0 power, we should know from Algebra 1, anything to the 0 power is what? Well, hopefully we remember that it is 1. Anything to the 0 power is 1. So we're going to use a calculator, guys. You're welcome to use a calculator today for calculations. If I have 65.3 and I take it to the 0 power, it doesn't matter what that number is. This didn't have to be 65.3. The answer will always be 1. Even something like negative 100.6, and I take it to the 0 power, that answer will be 1. And so all of these functions, when x is 0, the y will be 1. The general equation for all exponential functions can always be rewritten as f of x equals b times a to the x. Okay, so we've got our, here's our exponential part. And what's going to happen is the a will be the constant multiplier. We'll see why in just a second. And the b will be the y-intercept, the 0th term, the starting value. And depending on what the multiplier is, this could either be growth or decay. If the multiplier is bigger than 1, this is growth. If the multiplier is less than 1, this is decay. And this is because if you take any number, so let's take 100, if we multiply it by a number that is bigger than 1, the answer will come out bigger, 300. If I multiply by a number that is less than 1, so like something like 0.3, the answer will come out smaller. And so when you multiply by a number, remember it's a constant multiplier, so it'll multiply by that number over and over and over again. It will grow and grow and grow and grow and grow and grow. But if you take a number and you multiply, so let's start with 100 this time, and we multiply by a number that's less than 1, then what we'll see is it will get smaller each time. Shrink and shrink and shrink and shrink and shrink. Okay, so let's look at a table and see what's actually happening here. Let's do an example with y equals 2 to the x. This is a parent function, and so it will have the point 0, 1. So when x is 0, y is 1, because anything to the 0th power is 1. When x is 1, this is 2 to the 1 power, which is 2. Anything to the 1 power is itself. When x is 2, 2 squared means 2 times 2, which is 4. When x is 3, When x is 3, we'll put a 3 there. 2 to the third power means 2 times 2 times 2, which is 8. Remember, exponents tell you how many times to multiply by something. So 2 to the third power means 2 times 2 times 2, which is 8. What about when x is 4? What will y be? When x is 4, what will y be? Well, there's actually two ways we can get this pretty easily. One way is we could do 2 to the 4th power. 2 times 2 times 2 times 2. 2 times 2 is 4. Times 2 is 8, times 2 is 16. So hopefully we got 16. But there's another way we could have gotten this as well, which is by recognizing that there is a constant multiplier. Each time the exponent goes up by 1, there's an extra 2 compared to before. And so what you're doing is you're multiplying by 1 more 2 each time. And so 8 times 2 is 16, and we can use that to very quickly get to when x is 5. I mean, we could do 2 times 2 times 2 times 2 times 2, or you could just say, hey, it's going to be 16 times 2. So when x is 5, what's the y going to be? Well, it's 32, and we know that because the y value is just going to get multiplied by 2 again. Okay. What about negative numbers? When x is negative 1, this is 2 to the negative 1 power. And hopefully we remember from Algebra 1 or earlier this year that when you have a negative exponent, this means you divide by the positive exponent. So 2 to the negative 1 means 1 divided by 2 to the 1 power. So this is 1/2. 1 divided by 2. 1/2. When x is negative 3, for instance, this is 2 to the negative 3 power. When x is negative 3, 2 to the negative 3 power is going to be 1 divided by 2 to the third power. 2 times 2 times 2 is 8. So this is 1/8. But there's another way to think of it as well, which is that, okay, if we are, as we go to the right, as we're moving, have increasing x values, the y values are multiplying by 2. Well, if you think about going the other direction, 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 1. 2 divided by 2 is 1. Sorry. 1 divided by 2 is 1/2. 1/2 divided by 2 will tell us the one before it. So dividing by 2 is, half divided by 2 is 1/4. So, you know, when you go backwards along a table, you can divide. Now, let's look at what these graphs are going to look like. For the parent function, there will always be a point at 0, 1. Okay, so if there's just some number to the x, it will have a point at 0, 1 because anything to the 0 power is 1. As you go, let's do 2 to the x here. As you go to the right, we had a point at 1, 2. And then we have a point at 2, 4. Then we have a point at 3, 8. And what will happen is it will grow faster and faster and faster because every time you multiply by 2, well, the bigger the number it was, the more multiplying by 2 will do. As you go to the left, you'll be at 1/2, and then 1/4, and then 1/8. And what we're doing is we're actually dividing by a bigger and bigger number. Next will be 1/16, and we're getting closer and closer and closer to 0, and so there will be an asymptote. There's an asymptote at y equals 0. And of course, an asymptote means that you're getting closer and closer and closer to 0, but the y values will never reach 0. Dividing by 2, no matter how small the thing is that you divide by 2, there will always be something left. So like, I mean, look, we take 1 and we divide by 2, and then we divide by 2 again. And then we divide by 2 again, and again, and again, and again, and again, right? Like, it's getting smaller and smaller and smaller, 0.0007, but it's never going to get to 0 all the way. This is for a parent function. Now, it doesn't have to be a parent function. Remember that if you have something multiplying in front, that would be the y-intercept. And so, I don't know, maybe we'll start here. And remember, growth is when you're multiplying by a number bigger than 1. It could be something like decay, where we are multiplying by something that is smaller than 1, in which case it will go down. And if it does it like this, it will have an asymptote as you go towards 0 this way. It will still have a y-intercept. It'll still have a constant multiplier. It'll just have its asymptote. It'll also be at y equals 0. So this is what's happening, like if you're multiplying by, so in this case, I think the y-intercept was 5. So this is y equals 5 times, looks like I was multiplying by about 1/2 there. So 5 times 1/2 is 2.5, times 1/2 is 1.25, times 1/2 is 0.625, and we can see it's getting closer and closer to 0, but never quite reaching it, right? So it's got this asymptote going this way. On the other hand, when you divide, when you do a negative exponent, 1/2 to the -1 means 1 divided by 1/2. And dividing by a fraction is the same as multiplying by the reciprocal. So it actually multiplies when you go to the left. Okay, when we're in exponential equations, what we almost always want to do is find the equation, and we'll be able to use that. So to find the equation, we need to look for just two things. We need to look for what the constant multiplier is, and the other thing we need is the y-intercept. So let's see how this works. We'll start with a table and we'll try to come up with the equation, and then we'll move on to other things too. So here, to see if something is exponential, we need to look for a constant multiplier. If there is no constant multiplier, then it is not exponential. And so calculators are super helpful here. What we're going to do is we're going to look for a constant multiplier by dividing these two numbers. So 15 divided by 3 is 5. So that means that 3 times 5 is 15. It was multiplying by 5. Now we need to check, is 15 times 5, does that give us 75? So 15 times 5 is 75, times 5 is 375, times 5 is 1875, times 5 is 9375, and so this has a constant multiplier of 5. I hope we can see that. The other thing we need is the y-intercept. And so for that, we're looking for when x equals 0. That happens here. That number is 15. And so this tells me the equation is, remember, the general equation is y equals the y-intercept times the constant multiplier to the x. This is y equals 15 times 5 to the x power. That's the equation. And I hope we can see why, right? When x is 0, anything to the 0 power is what? Well, it's 1. So when x is 0, we'll get 5 to the 0 is 1. And so it'll be 15 times 5 to the 0 power. That's the same as 15 times 1, and 15 times 1 is just 15. That's what makes the y-intercept be the number that is multiplying, is because anything to the 0 power is 1. The reason 5 is the constant multiplier is every time x goes up by 1, you're multiplying by an extra 5. So like if we have 15, if x is 3, we've got 15 times 5 to the 3rd power, right? That's 15 times 5 times 5 times 5. Compare that to when x is 4. We'll have 15 times 5 to the 4th power. That's 15 times 5 times 5 times 5 times 5, 4 times, 4 5s. And there's an extra 5 at the end there, one more 5 that's multiplying, and that's why there's a constant multiplier of 5. Why don't you try this on your own? What is the equation of this table? And hopefully the first thing you did is to see if it's exponential, you tried to see, is there a constant multiplier? And so you can just divide these. 6 divided by 2 is 3. So this is multiplying by 3. 6 times 3 is 18. 18 times 3 is 54. You can use a calculator on these. Feel free to use it. So this is times 3 times 3 times 3 times 3. Great. So it's definitely exponential. The other thing besides the constant multiplier that we need is the y-intercept, and that's at 18. This is y equals 18 times 3 to the x. Here's our constant multiplier. Here's our y-intercept. Okay, this next one, I want you guys to try on your own, but it's a little tricky. There's one tricky thing about this, and I think you can figure it out, but we'll see. What is the equation here? Well, first, let's see if it's exponential. Is there a constant multiplier? It's multiplying by 2. It's multiplying by 2. It's multiplying by 2. It's multiplying by 2. So there is a constant multiplier. But the other thing we need is the y-intercept. And we don't have that here. We have 2, 3, 4, 5, 6. We need to go back. We need to go backwards to find what it was at 0. So we're going to go backwards. When x was 1, if you're multiplying by 2 going this way, it must be dividing by 2 going the other way. So when x is 1, y is 20. This was dividing by 2. When x is 0, we'll divide by 2 again and get 10. And so this was y equals, the constant multiplier is 2 and the y-intercept is 10. So 10 times 2 to the x. And I guess we shouldn't say y equals. This was f of x. So f of x equals 10 times 2 to the x. All right, guys. Hopefully we're feeling good about this. Let's try one more and see how we do. And move on to the some situations. So a ton of situations in real life are exponential. In this case, SpongeBob, this is maybe not a real life example. SpongeBob has plans to take over the world with an army of dolphins. Man, I wish I could draw better. I'd love to draw a dolphin. Here's a dolphin. I don't know. There's a dolphin, guys. Okay. That's not a very good dolphin. That's okay. Is that a better dolphin? Yeah, that's a little better. Okay. SpongeBob's going to take over the world with an army of dolphins. He has 4 dolphins now, but he plans to double that number each year. What does double mean? So he plans to double that number. That means it's going to multiply by 2 every year. This is a constant multiplier, right? This is a constant multiplier. Every year, they are going to multiply by 2. When will he have 1 million or more dolphins? Maybe that's how many he needs to take over the world, he's decided. Well, we want to come up with the equation, right, to be able to answer this. This is something we're always going to do. And the equation, we need to look for the constant multiplier. Here we have that. It's multiplying by 2. And we need the starting amount, that y-intercept. And that's how many he starts with. He has 4 dolphins now. That's when time is 0. No time has passed from now. So the equation should be y equals 4 times 2 to the x. Okay, he has 4 dolphins now, and every year it's going to get multiplied by 2. So every time x goes up by 1, you'll multiply it by an extra 2. Let's look at how this looks in a table. And guys, you can do this in a calculator to help you out. You can put y equals 4 times 2 to the x. If you don't have a calculator, that's fine. I hope you know on our homepage, on the main page of our blend, there is a place that walks you through how to get a good calculator on your phone. Or if you don't have a phone, there are other ways to do it too. Go look at our main page and click the calculator button to get a calculator. Oops, sorry. The table button is right here. It says table. It's in blue, so we need to press the blue second button. And here is the table. Oh my gosh. Let's go to table start. Oh my gosh, hold on. Where's table start? We want to start at 0. I don't know when the last time I was looking at this table was. Okay, so it starts at 4. We can see there's the y-intercept is 4. SpongeBob had 4 dolphins. Then he has 8 dolphins and 16 and 32. And guys, it starts out growing fairly slowly. But look, it's already in the thousands by the time we get to 10. Now we're looking for where he has 1 million, right? So we can just scroll down the table. And here we go. We had 524,000, so 524,288. This is not quite 1 million yet, right? It needs to have 1 more decimal place. The next number in here is 1.05 E6. This E6 does not mean the number is 1.05. This is 1.05 times 10 to the 6th power. That's what E6 means. So check it out. So 1.05 times 10 to the 6th power. It's because your calculator can't fit a certain number of numbers. So this is 1050, like that. And this is actually rounded. This is 524,288 times 2. You'll notice it's rounded from this number. That's okay. He will have, where was that in the table? We can see that after 18 years, be careful with this E number. When it has this E6, that means it's now in millions. And soon it will be E7. That's times 10 to the 7th power. So it'll be an extra 0 at the end. So these are the exponent that goes on 10 is what that means. I hope you know that from before. So it looks like 18 years. In 18 years, SpongeBob will have his dolphin army ready to take over the world. What does this look like on a graph? Well, if he starts with 4, that's his y-intercept, and it's going to double every year. So 1, 2, 3, 4. We probably should have counted by 4s. Let's make this count by 4s. Hold on, guys. I changed my mind. We're going to count by 4s. So 4, it's going to be 4, 8, 12, 16, 20, 24, 28, 32. And so he has 4, then he has 8, then he has 8 times 2 is 16, then he has 32. So this looks like this. His number of dolphins is growing faster and faster and faster. Now, guys, the graph will always be, let's go back to our main notes page. The graph will, if it's exponential growth, this is increasing, but it's always bending upwards. It's concave up. So increasing and concave up for growth. If it's exponential decay, well, going from left to right, this is decreasing, but it's still concave up. It's actually still bending upwards. You still have to bend it upwards. So it still has this bending up shape. So all exponential functions are concave up. They all have a y-asymptote at y equals 0. You'll notice whether it's domain, whether it's growth or decay, the domain is always all real numbers, so all the numbers between negative infinity and infinity, because you could do any number to a negative exponent, and the range will always be all the y values that are above 0. But don't include 0. Notice we did not put greater than or equal to, because there is no y value at 0. It's only the y values above 0. Okay, so we were able to answer this question in this way. You actually can also answer it on a graph, but I'm not going to get into that right now. This is going to be our last example for the day. Maria, let's do a money example to like whet our taste for tomorrow. Next class, we'll talk a lot more about money. Maria has $50,000 invested in an account that grows by 5% each year. How long until she has $60,000? What about $70,000? 50,000 plus 10,000 gets her to 60,000. 60,000 plus 10,000 gets her to 70,000. Will it be the same amount of time? Let's see. What is the equation going to be here? Well, is this a constant multiplier? And the answer is yes. Growing by a percent, the way we grow by a percent is we take the 50,000 and we add in 5% of 50,000. So 5% is 0.05. Remember, you can always get a percent to a decimal by dividing by 100. So 0.05. So growing by 5% means we multiply by the original amount by 5%, and we add it to her beginning amount. So look, here's 50,000 times 5%. It's $2,500. That gets added to her original amount. Okay. So, but to grow by 5% the next year, you're not adding another 2,500. What's going to happen is the next year, the 5% is going to be 5% of, oops, that's one extra 0, 5% of her new amount. So we're going to multiply the new amount by 0.05 and add that into that new amount. Now there's a much easier way to do this, which is we can factor. What we're doing here is we're factoring, we're going to factor out the 50,000, and it's going to be 50,000 times 1 plus 0.05, or 50,000 times 1.05. This is how we grow by 5%. This is grow by 5%. What's happening is you're multiplying by 1 to get you back to where you were, and you're adding in 0.05 times 50,000 to go up by 5%. And you'll notice that I could have gotten to this answer by just doing 50,000 times 1.05. That gets me to 52,500. And we can do times 1.05 again, because that'll grow this amount. It'll multiply by 1 to get you back to where you were and add in the 5%. And that's a much faster way to do it. So we could just multiply by 1.05 each year, and that's our constant multiplier. So this is a constant multiplier of 1.05. So let's look at what happens here, guys. We are going to see when she gets 60,000. Let's use our table again. Y equals 50,000 times 1.05 to the x. And we'll look at our table, and here we are starting at 50,000, then 50,000, 52,500. She gets to 60,000 after 4 years, right? So it takes her about 4 years to go up by 10,000. Does it take her another 4 years to go to 70,000? Let's see. She's at 70,000 in 7 years. It only took her 3 more years to go up to 70,000. And that's because the more you have, the faster it grows. The way exponential functions work is you grow based on how much you already have, which makes sense, right? You're growing by 5% of what you have. And so to go to 60,000 took more time than to go to 70,000. All right, the last thing is, what if you have a graph? How do you find the equation? Well, if you see that exponential shape where it's got an asymptote, we're going to look for a constant multiplier. In this case, this has a constant multiplier. Let's see, this is 4, this is 8. It's going down, so this is multiplying by 1/2, a number less than 1. Dividing by 2 is the same as multiplying by 1/2, right? Dividing by 3 is the same as multiplying by 1/3. So multiplying by a fraction is the same as dividing. Okay, it got divided by 2. Going from 4 to 2, I can see this y value is 2. It got divided by 2 again, then it goes to 1. I can see it's dividing by 2 each time, and so I can see my constant multiplier. I also can see directly on the graph what the y-intercept is, and so I can write the equation. This is y equals 4, that's the y-intercept, times 1/2 to the x power. Now there's a cool way to write 1/2 to the x power. This can also be rewritten as 2 to the negative x power. And this is because negative exponents tell you to divide, and dividing by 2 is the same as multiplying by 1/2. So I'll do an example on that real quick. All right, what is the equation? This point is 2, 9, in case you can't see. What is the equation of this graph? And hopefully you notice that the y-intercept is 1. This is 3. It's 1, 3, right? So the multiplier going from 1 to 3 is 3. Going from 3 to 9 is 3. So it's got a constant multiplier. And because the y-intercept is 1, this is just y equals 3 to the x. It's a parent function. Remember that if it goes through y equals 1, if that's the y-intercept, then it's a parent function, and you don't need a constant multiplier. You could put 1 times 3 to the x, but 1 times anything is itself, and so we write it in the simplified form. That's it for today, guys. Hopefully you get some good practice on our homework tonight on writing these exponential functions. This is a super important real-world idea, and we're going to get into many more real-world examples next class. Specifically, we're going to be dealing with money. I hope you guys have a good rest of your day. Bye.